the basics, but there is disagreement about what it means. There's a famous quote from George Orwell, which I always like, referred to English: "A man may take to drink because he feels himself to be a failure, and then fail all the more completely because he drinks." It's rather the same thing that is happening to the English language. It becomes ugly and inaccurate because our thoughts are foolish, but the slovenliness of our language makes it easier for us to have foolish thoughts. In any event, global warming, to be honest, is about politics and power rather than science. And that's almost immediately clear. In science, there's an attempt to clarify. In global warming, language is misused in order to confuse and mislead the public. For example, the expressions skeptic and denier are meant to suggest there is a strong case for climate alarm. Hope to show that this is really not the case. And I specifically emphasize alarm. Nobody is talking about climate change or anything else like that. The misuse of language extends to the use of models. For the advocates of policies allegedly addressing global warming, the role of models is not to predict, well, see, they don't do that, but rather to justify the claim that catastrophe is possible. Of course, proving something to be impossible is itself almost impossible. In a further abuse of language, the advocates attempt to rephrase issues as yes-no issues, and this you find frequently in the media. So, for instance, yes-no questions like, does climate change? Is CO2 a greenhouse gas? Does adding greenhouse gas cause warming? Can man's activities cause increases in greenhouse gases? Now, the trouble with these is they're meaningless as concerns alarm. For science, as Lord Kelvin long ago pointed out, you need to have how much questions. This is certainly the case for the above questions, where even I would answer yes to all of these. Okay, so where are we? Well, we're at a very peculiar point. To a certain degree, you can't really discuss this issue anymore because people are using words in radically different ways. That said, there are certain things basic to alarm. One of them is that alarm requires that the climate is highly sensitive to added greenhouse gases. And the basis for this is purely computer models. The relation of this sensitivity to catastrophe, moreover, does not even come from these models. It mainly comes from the imagination of climate activists. I'll go into this in much more detail tonight when I go over what different people say. But here are some of the questions that are relevant to a study of climate, at least in my opinion. One is, what is the sensitivity of global mean temperature to increases in greenhouse gases? A second question is, what, if any, connection is there between weather events and global mean temperature anomaly? I use the word global mean temperature anomaly because that is really what is used in all the diagrams. There is no meaning to global mean temperature, but what you do is look at the deviation at each station from its mean over a 30-year period, and you average these deviations. Another question is our understanding of the greenhouse effect adequate? Well, see, there are some serious problems with that. How relevant is the simplistic notion of some global mean radiative imbalance driving global mean temperature to actual climate change? One of the things, and I won't have time to go into a lot of detail on this, but for instance, some of the major changes in climate in Earth history, like the Ice Ages, or the Eocene, or things like that, the Cretaceous period, are most easily explained with something other than some mean forcing. The Milankovitch hypothesis turns out to be extraordinarily good, and it really has nothing to do with that. Now, obviously, I'm not going to cover that in an hour, and I'm going to rush through some of this. As I mentioned, for any of you who want the details on these slides, they're available as a PDF file, and anyone who wants them can just email me. At any rate, if you start with some basic physics, and this I'm sure most of you are familiar with. Now, let's say you had an Earth that had no atmosphere, you have the sun. You're simply saying to have a thermal equilibrium, the radiation captured, I wonder if the arrow works on, no, it doesn't. Okay, so I have to use this device. Okay, so, you have a cross-section presented by the Earth. It intercepts the Planck radiation from the sun, characterized by the temperature of the sun, which is about 6,000 degrees. And then the Earth emits radiation at its temperature over its whole area. And when you do this, if you don't assume that the Earth reflects sunlight, you get that you reach 272 degrees. And if you say that there is an albedo of about 0.31, then you get 255 degrees. Now, you've all probably heard that the difference between 255 and 288 is the greenhouse effect. The thing to remember about this is if you're looking at the Earth from space, this is the temperature you would see. So what's happening is the Earth is emitting radiation from some level other than the surface. But since the temperature must decrease with height, the surface ends up warmer. Okay. Now, there's one last thing here I'll mention. Namely, this already gives you a handle on something about CO2. CO2 doubling is about a 2%, actually it's a bit less than 2% of the radiative budget. And if you change the solar output by 2%, you'd get about 1 degree change in this temperature. So that per se is never considered terribly dangerous. To actually see how the greenhouse effect works, you have to think about the lower atmosphere as a turbulently mixed slab of air. The turbulent elements are cumulus convection in the tropics and something called baroclinic instability in mid-latitudes. These redistribute heat and so on, they transport heat, and they create the temperature structure in the vertical. Now, essentially, I think the next slide may, wrong. Now, getting back, I forgot this emission temperature, 255, is a temperature somewhere around here. So it's saying the atmosphere is emitting from some level. It's called the characteristic emission level. I'll criticize this notion a little later. But it's one optical depth, in a crude sense, into the atmosphere. So if you go deeper, space can't see it. So it sees it characteristically at some level. Okay, that's within the troposphere. Okay, so essentially to get it to emit from an upper level rather than the surface, you need greenhouse gases. These are gases that absorb in the infrared. Water vapor is the main such gas, but there's CO2, methane, ozone, they all contribute. Clouds also, upper level clouds, are crucial greenhouse substances. They are really the most powerful, but of course we don't have 100% cloud cover. If you don't have clouds, then, this is your emission level in principle. It's about 5-6 kilometers. However, when you do have clouds, the top of the cloud is the emission level, because that's over 1 optical depth there, as you rule. If you add greenhouse gases to the atmosphere, what happens? Well, because the temperature is decreasing with height, you are reducing the emission temperature, and it no longer balances the incoming solar radiation. So the whole system has to warm. And because it's dynamically mixed on a short time scale, the whole troposphere has to warm as a whole, including the surface, while preserving its lapse rate. This refers to the rate at which temperature decreases with height. That's crudely correct. This is a picture of what's going on there. In mid-latitudes, the lapse rate is about 6.5 degrees per kilometer. In the tropics, it's something called the moist adiabat, and that's important. It's somewhat different. But the idea here is the following. Here is your greenhouse gas. Tau equals 1 is 1 optical depth into the atmosphere. In the unperturbed, equilibrated case, the outgoing infrared equals the incoming solar, net incoming solar, minus the albedo. When you add greenhouse gas, you elevate this level, let's say from 350 to 300 hectopascals. Now the outgoing infrared is smaller than the net incoming solar radiation. And so in order to restore this to this value, the whole system must warm. The moist adiabat turns out to be somewhat important in this, but we won't discuss this at much length, because it says that the temperature change at the upper levels of the troposphere is going to be appreciably greater than at the surface. And that's the so-called hotspot problem. That's an interesting problem. One does not observe this in the data, but all the models do produce it. In any event, this is the simple depiction of the greenhouse effect. Radiative forcing, as used by the IPCC, refers to this imbalance here. And so, for instance, if you double CO2, the imbalance produced is about 3.5 watts per meter square. And as we saw before, that roughly corresponds to 1 degree centigrade in change. That's the non-feedback value. As I said, climate sensitivity refers to the equilibrated response of global mean temperature anomaly to a doubling of CO2. The doubling is purely a convention. Everyone uses that as a measure. And as I say, in the absence of feedbacks, this is approximately 1 degree centigrade. There are problems with the notion of characteristic emission level. They're illustrated here. Where you have cirrus clouds, it comes from the upper level cirrus clouds. This is from the characteristic emission level for the gases. You have a window where the surface can actually see space, although both CO2 and clouds close the window. But you do have emission from the surface as well. The clouds complicate things because they not only change the emission level, but they also reflect shortwave radiation. Although there are thin upper-level cirrus, so-called invisible cirrus, Vern Suomi discovered these many years ago, where you have a large infrared opacity and almost no reflectivity. So you don't even see these clouds. When clouds are below the characteristic emission level for gases, they don't change the impact of greenhouse gases, but if they're above, they have a profound effect. At any rate, there is a tricky issue when you have clouds, because if you have cloud coverage on the order of 35%, especially in the tropics, typical altitude for these clouds might be 10 kilometers. There, the temperature is about 223 Kelvin. And thus, the characteristic emission level away from these clouds would be 268 degrees to reach 255 for the whole thing. And that's, often ignored in the picture. We may come back to that. As I say, most calculations of radiative forcing due to CO2 ignore the shielding effect of upper level cirrus. I would say, as a crude approximation, don't worry about this too much, you probably are better advised to use 3 watts per meter squared for a doubling of CO2. There's a physicist, a molecular physicist at Princeton University, Will Happer, a rather distinguished person. He's recalculating the effect of CO2. There's a reason to do that. The models use a relatively simple model of CO2 wings. As you know, you might have an absorption line and then it has wings that tail off as you depart from the center. The treatment of these wings is very important because the CO2 is already blocked in the center, so its effect on climate is coming increasingly from the wings. It's not a huge effect, but it would probably knock this down another 30%, its effect. But what we'll look at here is, what does 3 watts per meter squared do? Before doing that, I'm going to mention something that is often ignored. What kind of changes in the atmosphere can produce 3 watts per meter squared? It's a small amount, as we say. It's a couple of % of the radiative budget. So for instance, a 10% change in the area or a 500-meter change in the altitude are enough to change the radiative imbalance 3 watts per meter squared. Now, it turns out that in normal activity of the atmosphere, changes bigger than this are normal. Now, why do I mention this? Well, it's because, if these changes are due to surface temperature, we call them feedbacks. But there are lots of things that can cause changes of this order. As I say, they're routinely happening in the atmosphere all the time. And in physics, the proper way I would suggest to deal with this is as degrees of freedom of the system. What that means is the system has within it the ability to adjust to such changes without much difficulty in the normal course of events. And we'll see that in turn has an important effect when one comes to the Milankovitch hypothesis. Okay, turning to feedbacks. Let's say we have a system, this is just a node. You're forcing it with a certain heating. Here is the system. Its no feedback gain is G0. And in this electrical engineering view due to Bode, the change in temperature would be G0 times delta Q. When you have feedbacks, then delta T produces an additional flux that's fed back, so that at the end, the change in temperature, if you can see this, is the original no feedback change divided by 1 minus the sum of the feedbacks. Usually it's written this way with the summation sign. Now, there's a curious thing about this. You notice what happens when the sum of the feedbacks equals 1. What happens? The answer goes to infinity. That's a little bit absurd. You can even go beyond 1, and then for the electrical engineers here, if there are any, you go into an instability. The system runs away, and eventually in the real system it would be controlled by nonlinearities. It doesn't go away forever. I mean, obviously. Here's a sort of a picture of how it works. You start out in balance. You've added the greenhouse gas. It changes the temperature changes the greenhouse gas and exaggerates the imbalance. I won't go into this in much detail, but of course you have to remember this is in models. In the real climate, the feedbacks could well be negative. They don't have to be positive. There's nothing about that in nature. In fact, in nature, negative feedbacks are the norm. Now, here is a picture of that 1 over 1 minus f, as f goes from -2 to +1. As we see at +1, it blows up. Now, the thing to recognize in this is when you have positive feedbacks, this pink region here, very small changes in the feedback factor give you big changes in the response. When you have negative feedbacks, it's a very different situation. Then, you can have very big changes in negative feedback, and it always remains roughly in the same part of the domain. Degrees of freedom that I mentioned are all sufficient to provide feedback factors between plus and -1. Now, in current climate models, they always refer to a water vapor feedback. We'll have something to say about that later, because by now I think almost everyone who works on this, on either side of the issue, agrees we don't have that. And so that's kind of interesting. The point is, when you do have that, it starts you out here, okay? And so you start out here, and 1 over 1 minus a half is a half, so you double the response. But you don't have to add very much to it to go to 5 degrees, to go to even infinity. And so you'll all perhaps remember the IPCC says the range of sensitivity is 1.5 to 4.5 degrees. That's saying you're just hovering a little bit around here. Sounds like a big range. Now that range has not been changed since 1979. There's another thing I want you to remember about this feedback, and I hope I'm not stretching out too far. It is the ratio of a change in temperature to a change in flux. That has an important implication, because it's the change in flux that changes the ocean temperature, okay? And if you have a high sensitivity, you have a large delta T associated with a small delta F. What that means is it takes longer to reach equilibrium the more sensitive you are. That plays an important role in a lot of things. Okay, now there are a lot of papers that try to infer sensitivity from the temperature record. It's not really possible for reasons I'll mention, but the record is in fact suggestive, and we'll see why. And I'll rush through this, but here's the IPC, has this iconic comment that most of the warming due to the last 50 years or so is due to man. I'm going to discuss this further tonight because that's a very weak statement. It says, about a little bit over half of a half degree in the last 50 years is due to man. This should not be a matter of alarm. I mean, you can't perceive a quarter of a degree. But the argument runs as follows. They say if they run their models without greenhouse gases, this is what they get. And so and this is what you observe. So you have to have greenhouse gases added to see what you observe. Underlying this is an assumption, a very serious assumption. And that is that you have models that account for all sources of warming. And in particular, it assumes that the models correctly display what is called internal variability. Now, we know there's internal variability. We'll see that in a moment. And the models don't reproduce it. And so the argument is on weak grounds. We have a little model that the IPCC also uses to examine this, to see what in the world this really means. Let's go through that briefly. Here's the IPCC list of radiative forcing. The only difference, this is the AR5, the latest one. They show very uncertain, but actually much less uncertain than they used to, aerosol. Aerosols can themselves reflect or absorb sunlight. They can also affect clouds. And what the IPCC doesn't include, although it has it in the text, this is often curious with the IPCC, the text mentions that under freezing conditions, when you have supercooled clouds, adding aerosols can actually instead be a warming effect. So the uncertainty actually has a range on both sides, at least within the known physics. There have been improvements in this in recent years. The anthropogenic effect, according to the IPCC, includes not only the greenhouse gases, but the aerosols. And that's a dodge. We'll see later. That's sort of a way of adjusting away any difficulties. Okay, so here is a simplified but totally adequate picture of the total greenhouse effect forcing as a function of time from 1800. We see it remains small, and then it's growing in the period after 1950. It's reaching something under 3 watts per meter squared. So it's already reaching something like 80% of a doubling of CO2. So it's not as though that's a remote number in the distant future. We're there. We've seen about 3/4 of a degree. Now, the IPCC models also are subject to volcanic forcing. And most models use the model developed by Sato at the Goddard Institute for Space Studies. There's uncertainty, but it's as good as any model as far as I can tell. You see that volcanoes are clustered. There's one group around the late 19th century, early 20th century. There's a gap in here. There's another sequence that are more recent with Pinatubo. Something curious, it's irrelevant to many things. There's nothing special about clustering. It is the normal behavior of a random process. People always look for an explanation. Why did it cluster? There may be no explanation. Because, think about flipping a coin. What are the odds of getting head, tail, head, tail, head, tail? That's 0. So you're going to get clustering. This is the model. The model consists in a simple thing where you have land, you have ocean, you have transfer between them, and in the ocean you have a mixed layer and you have diffusion into the thermocline. Usually you base the diffusion coefficients on carbon measurements from tests, nuclear tests, things like that. There's upwelling, which stops the diffusion at something called the thermocline. Wouldn't worry much about it. You can look at it more carefully in the references. The flux at the surface is not radiative, but because you have fixed the profile due to the mixing in the troposphere, the divergence of the flux should be approximately zero. So the flux here might not be radiative, in fact it's turbulence, it should be the same flux as at the top of the atmosphere that's radiative. At any rate, using this model, keeping in mind the change in response time. Now you have an ocean, you're looking at a time-dependent system. You can now calculate. So for instance, let's say we're calculating the response to the CO2 change using this simple model. The difference between these energy balance models and a GCM is in the energy balance model, you specify the sensitivity. In the GCM, nominally, it's supposed to come out of it internally, but it depends on cloud processes, which the GCM can't resolve, so that's parameterized, and there's a whole mess associated with it. But all I want to say in this is, if I have a sensitivity of 0.75, and I assume all the warming is due to man, then I don't quite meet it with 0.75. I exceed it with a sensitivity of 1.5, and the others are well above, but not as far above as you would guess from the equilibrium sensitivity, because it takes time. So I don't have time in each one to achieve the full difference. This is just this remark. Now this is the response to the volcanic forcing. And that's usually ignored, but it's kind of cute in a way. If you look at the sensitivity of 0.75, then the volcanoes just give you blips where you have a volcano. But if you get to high sensitivities, and it's just more than 1.5, even 1.5, you begin getting a memory of the volcanoes that leaves you with appreciable cooling even after many years. And this gives you about 0.3 degrees centigrade cooling for high sensitivity. So if you combine the volcanoes and the greenhouse gases, and both of these are in the models, then you get this, and this is roughly what today is. So again, you're sort of slightly exceeding it with 1.5. You're substantially exceeding it with more than 1.5 degrees sensitivity. Now, that isn't what you see usually. In fact, all the models end up describing the past correctly. How do they do that, given their different sensitivities, and given that the sensitivity should lead to different results? They do that very simply. They subtract whatever heating they need with the aerosols. And so this is the amount of aerosol you have to subtract. Remember, we're starting with 3 watts per meter squared. So this is taking away 3/4 of a watt per meter squared. Here you have to take away, for these, around half. Again, the difference is less than you might suppose because of this time effect. Now, here you're beginning to see a problem. There's been a recent paper by Bjorn Stevens at the Max Planck Gesellschaft, and he has been trying to narrow the uncertainty on the aerosols. The IPCC in the last version also reduced the uncertainty so that these were marginally out of the picture. Bjorn is suggesting the most likely value for the aerosol effect is no more than 0.5 watt per meter squared, but it's possible it might be as big as 1. 1 is still not enough to cover these. And so essentially it's pointing to the fact that sensitivities in excess of 1.5 degrees are almost impossible. And this is assuming we're accounting for all the warming. Remember, the IPCC statement is more than half. Let's say it was 49%. Then even 1 degree centigrade is problematic. So how would you now argue for high sensitivity? Well, there is a way, unfortunately. Let's see, do I talk about this? Yeah. We'll come to this in a moment. First, even looking at the temperature record from the Hadley Center, and I put this pink fuzz on to show you it's not precise. There's always a few tenths uncertainty in it. But this is from 1850 to the present. You notice there's no sign of a prolonged volcanic effect in this. It's hard to tell what that means because there are so many adjustments in the models that you never know what they really had in it. But you at least don't see anything obvious from the volcanoes. There was a paper in 2013 suggesting that about half the warming was in fact due to internal variability. That would leave you, again, with a problem. The difficulty with the internal variability is you know it's there, you don't know what it is necessarily. So what I imagine will happen at the next IPCC is they'll assume that the internal variability, instead of accounting for half the warming, canceled half the warming. And that will leave you again with something that might allow it. It begins to get harder and harder. Now, here's the real problem that's been pointed out in recent years, that since about 1997, there's no significant warming. And the models are predicting ever-increasing deviation. And this is plotted since 1975. It's not recent. The models are generally lying well above anything in the observations. Now, what does this mean? It means a number of things. It means, one, the models aren't accounting for what we see. And the reason might be, and should be, I think, most likely, is it's saying that there's something else going on that's at least as big as the greenhouse warming. But that, if it serves no other purpose, tells you, I mean, this is, that the argument for the iconic statement is incorrect. Because that assumed that there was nothing competing with the greenhouse forcing. The fact that you don't see the warming that the greenhouse warming is supposed to produce says there's something at least as big. Okay, now it's also a matter of engineering here. If engineers were to see models like this, and this is the observations, at the very least they would consider these models better than these models. But the IPCC is democratic. And so there are models from all over the world, and they just take the average of all of them without asking, is one better than another? So they use this as the quote, most likely. Okay, now, are there ways of pinning down the sensitivity? And this, I won't be able to go into in much detail. There are ways, for instance, the time scale itself with the volcanoes. Gerard Rowe in 2009 suggested that you could use the Pacific Decadal Oscillation, which has a characteristic time, actually 1.5 years, not 10 years. Run the models, see what the time scale is for it, how does it compare with the observations. You can do that, and there was a student from the École Polytechnique who looked at this a few years ago. You did find that the model response times were longer than observed, but you also never knew how the models treated the ocean. And so you never knew if it was due to a change in the ocean or sensitivity or whatever. Another approach was done by Nir Shaviv. And what he did was very clever, and I don't think it's gotten enough attention. You can show that there is a component of the ocean temperature that correlates very well with the sunspot cycle. You know the temperature change in the ocean. You know what flux was needed to create that temperature change. That then tells you what amplification of the solar output was needed, presumably by cosmic rays. And you can use that to infer sensitivity. That gives you about 1 degree. There is also an attempt that I did with Young-Sung Choi and so on, which was to use temperature fluctuations observed and compare it with radiation measured from satellites. And that turned out to be rather problematic. I won't discuss it much here, given the time. You have to look at specific timescales to avoid certain problems, but it was another problem that was really difficult. The outgoing radiation depends on clouds, and clouds depend on a lot of things other than temperature. So you never know if you're dealing with noise. It turns out in a paper in 2013, where is it here? Choi et al., 2013, that we discovered by just using Monte Carlo tests with lots of noise that there was a certain characteristic curve for the response if it was a high noise response, and if there was a high signal to noise, you got a different response. This is crudely, and those who want the details, I'll be glad to give it. Here is the long wave response, and here's the short wave response. Turns out the S-shaped curve for short wave indicates you have a high noise. And so you don't know what this means. Where you have a single maximum in the correlation and in the long wave response with a lagged correlation, that indicates a feedback. In this case, the long wave feedback is negative. Now, why do I say long wave? The water vapor feedback is long wave, but you cannot distinguish it from the cloud feedback from the cirrus, because it only applies where you don't have cirrus, and the cirrus is varying all the time. So what you have to do is combine the two, look at one feedback in the infrared, and that has the combination of both. This is saying it's negative. You can argue about that, but the one thing that you can't argue about is when you take the model into comparison data and you ask what would the models do with the same temperature, they get a positive feedback and not a negative feedback, and they get something very different from what's observed, which at the very least is saying their feedbacks are incorrect. Now, you notice, going back to this curve, if you don't start out at 0.5, but you start out at 0, then the changes that gave you the range of 1.5 to 4.5 now all give you very little amplification, even if they're real. So if you get rid of the 0.5, you've gotten rid of high sensitivity. Now, I won't go into much detail, but there are a couple of things. The issue of what can cause something to change in the cirrus is often associated with what I call the iris effect. That's been argued a lot. It's been confirmed by a lot of independent studies. And most recently, again at the Max Planck, they showed that they need essentially a cirrus effect to bring the model into agreement in various details with the observations. So I think it's looking good for that. Let's leave it at that. I think we now can see that high sensitivity, which is essential for catastrophism, really requires very special pleading. You need to overcome the aerosol problem. You need to have either that or natural variability coming in just the right way at the right time. This is getting a little dicey. What about extreme weather? Well, you know, it's funny. outside of the tropics, we depend on baroclinic instability. That determines the intensity of storms, the variability, the extremes. And what is baroclinic instability? It's measured by the equator to pole temperature difference. Every model says, what happens to this difference in a warmer world? It doesn't get larger, it gets smaller. So, it's hard to tell where the extreme stuff comes from. And as we'll see tonight, even the people at Goddard Institute for Space Studies say this comes from no place. Okay. This is sort of also, it's talking about extreme weather. And every day in Boston, in the Globe, this is 2013, they publish a graph like this. It goes back 30 days. And for each day, it shows in blue the high and low temperature for the day. Dark gray is the climatological high and low for the day. And the light gray are the extreme, the record-breaking highs and lows for that day, occurring some other year, usually. Now, that's all well and good. And then there's this red line here. And what is that red line? Well, that red line, the thickness of it is, no, I don't have the picture here. That's the whole range of global mean temperature anomaly for the last century and a half. So when you say you feel global warming, or you feel cooling, or you're fooling yourself, okay? That's nowhere in this picture. This is a map of temperature for North America. You can do the same thing for Europe. It turns out this is the map for this day, or the 11th of March, 2013. It turns out the record-breaking high and low for that day, which occurred many years ago in most cases, 39, 62 or 61, is the highest and lowest temperature on this map, roughly speaking. Which is to say, what causes the high and low extremes? It is the carrying of air, the advection of air from a place that's hot or a place that's cold. It's not any global process. And that, again, the intensity of the airflow associated with it is the eddies, the baroclinic eddies, and that gets weaker in a warmer climate. Okay, now, there are other things, evaporation, and I'll skip that. Now, I think the questions that matter strongly, namely sensitivity and extreme weather, both of them fail to be plausible. They both depend a lot on hypothesis, and in the case of extreme weather, it's nonsense. But it's sometimes claimed that paleoclimate points to high sensitivity, meaning ancient climates. And here I'm going to just rush through this, but you have the fact for the past 700,000 years, there's this 100,000-year cycle of ice ages. 90,000 years of ice, you have the Thanoscandian ice sheet over you, and then you have 10,000 years of interglacial. And a Serbian astronomer suggested this might be due to the orbital variations, the variations of the ellipticity, of the tilt of the axis, the eccentricity. Anyway, you go through this, and you have these various variabilities. I'll skip over this. There was doubt about the Milankovitch hypothesis for many years. Not many years, but after a program called CLIMAP. And it's a sign of how primitive our subject is. Remember, this is not a well-developed science, climatology. It is a backwater science. People have tried, the data is poor. It's a hard thing to deal with. And for many years, the people studying it compared ice volume with the Milankovitch parameter, and the parameter was insolation, the incoming solar radiation in summer in the Arctic. Now, he wisely chose this because that determines whether a glacier survives or grows. You always get cold in the winter, and you always get snow. But if it's too warm in the summer, it doesn't last, and so no glacier builds up. If it's colder in the summer, the snow survives and builds to the next year and the next year and the next year. Okay, so all of a sudden, three young Swedish astronomers realized there was an error in this. You compare the insolation, the Milankovitch parameter, with the time rate of change of the ice. All of a sudden, the correlation is as good as anything you have in geophysics. And this was rediscovered in 2006 by Gerard Rowe. And I picked his curve because he shows the anomaly in the radiation associated with the Milankovitch parameter. And it's on the order of 100 watts per meter squared. Remember, we're talking about 3 watts for doubling of CO2. Or if you look at the ice cores, you're looking at 1.5 watts per meter squared for the variation in CO2 that they measure. You know, and this brings us to degrees of freedom. Here you have something, 100 watts per meter squared. It's correlating perfectly, and it's the right amount of heat to account for the melting of the ice. You couldn't ask for more. And yet, the prevailing notion is it's the 1.5 watts per meter squared that drove this whole thing, ignoring the fact that the degrees of freedom in the system are such that it's trivial to balance this sort of imbalance. I would suggest that favoring this hypothesis has inhibited progress in climate science a great deal. Okay, now, the last thing I want to mention, and it'll be only a few minutes, no one, certainly not me, is an expert in all aspects of climate. And so, for instance, if you're involved in the physics of climate, one thing you're not terribly up on usually is the geochemistry of carbon. And so what do you do, including myself, if you don't know about something? You assume what you're hearing is right. Now, we've all been told that we know that the increase in CO2 is due to man. What do you do if you're not an expert and you're told that? Well, the simplest thing is just believe it, but you might look at some things and see how plausible it is. I mean, we do have data on bomb test carbon-14. You know, after the test ban treaty, you suddenly shut off this source, and so you could watch how it relaxed. And it relaxed with a timescale of 10 to 20 years. It was pretty precise. The IPCC uses a model they call the Bern model, which has only 2 empirical inputs, the Keeling curve for increasing CO2 and the estimated human emissions. So it doesn't even deal with the bomb test, and it doesn't fit it. Well, that's one thing that would worry people. It worried Murray Salby. I think he was right. The other thing that worried him, which I think was correct, we know from the International Energy Agency that around the early 21st century, there was a marked increase in the rate of increase of emissions. And yet, when we observe CO2, there's no change in that. I would suggest at the very least, from the policy point of view, this suggests we don't know how to control CO2. If the CO2 in the atmosphere doesn't reflect what we're doing. And then, before 1958, all we had was ice cores, and at least again at Goddard Institute for Space Studies, which is certainly one of the most supportive institutions for alarm, they find that the earlier behavior of CO2 increasing from 280 and then increasing, has a robust feature here of a dip in CO2. And the problem with the ice cores is the dating is not precise. There's about an 18-year or something, they say, spread, according to the articles. But that allows that this CO2 really coincides with that brief cooling period that was between 1940 and 1978 or so. And that's saying if CO2 itself is partly dependent on temperature, then we really don't know how much of it is due to man. Again, I don't know the answer to this, but it seems that anyone who's viewing it as a scientist is obligated to examine the issue, not just me, but you as well. And the question, do we know how to control CO2, is a crucial one for policy. Hey, here's my last statement. I think we've seen that climate is probably insensitive to increases in greenhouse gases. That doesn't mean that there is no sensitivity, but it's, unlikely that it'll be great enough to be catastrophic. We also see that, a warmer world should not be characterized by more storminess and extremes, though both are part of normal weather variability. Here I would say the models are probably correct. They don't show this either. This is purely, I think, part of the propaganda. And as I say, there's even reason to suppose we don't know how to relate emissions to atmospheric CO2, which makes policy very difficult. When you speak of the consensus of scientific agreement, what you're talking about are those yes-no questions I was talking about, and they don't tell you that there's a catastrophe. So the one thing that disturbs me in this more than anything is that this misuse of language has been something that the scientific community has accepted. And that's disturbing for both science and society, to say the least. So thank you for your attention.
Thank you very much.
Okay.
This was very interesting, I think, for us to hear from a person that has worked with this for so many decades.
Yeah.
I'm open for questions
Sure.
now. Yes?
One of your main points.
Can you say your name before?
Jon Egil Christensen, Professor of Meteorology.
Yeah.
I think
Yeah, sure.
one of your main points that you're making is that the climate models have climate sensitivity which is much larger than you argue that it should be. Well, I mean, those of us who read the literature, we know that pretty much all estimates, both observation-based and model-based, are much higher than yours. So it's much.
You'd say that, but let's get down to specifics.
Yeah, okay, let me get back to my question. My question is, you had one figure where you showed the temperature evolution of the last 40 years.
Yeah.
And you had several curves for the models, and you had some dots for observation.
Yeah.
And could you show that figure?
Sure. Sure.
Yes, thank you. So is this surface temperature?
Well, we could have used surface temperature. It gives you about the same.
No.
Yes, it does. It gives you something.
The temperature change.
No, you.
Half a degree, which is
No,
what the models are showing.
no, I disagree with that. That's nonsense.
Well, you could go back to the Hadley Center. You had it before, the Had crew.
Yeah, but the HAD crew.
You had it in a previous one.
Yeah. Let's see, which way do I go on this? Yeah. Here's where we are now
Yeah,
on
so
this.
half a degree, which is exactly.
No. That's not true. That's just not true. First of all, comparisons can be, here we use the models for the same thing we took the data from. Other people have used the surface. The surface itself, according to Hadley, according to GISS, also has remained fluctuating, but no trend greater than about 0.1 degree in that period.
No, I mean, the Hadley Center.
Oh, that is simply untrue. No, that's simply
There's
untrue.
no discrepancy between the models and the observations.
That's not true. And at the very least, how should I put it? You would have to say that some of these models must be disagreeing, and this is disagreement in at least this parameter.